Okay, so let me remind people that will be a group photo immediately right after this talk. And I guess everyone's supposed to assemble out on the patio out here.
The balcony. The
Balcony.
balcony.
Oh, it's a
Yeah.
balcony. Okay.
Yeah, the balcony.
The
yeah.
balcony.
Balcony by the back door.
Okay, thanks, Paul.
Oh.
Okay, so the last speaker of the morning will be Paul Selick from the University of Toronto, and he'll be speaking on the work of Fred Cohen, first 25 years.
Thank you. Am I using this correctly? The microphone is working, good. So I've never done one of these things with a microphone before. So, okay, there's an old message that's outdated that says we can hear you. Is there an update? No, I did switch it on. I did switch it on.
Yep, you're good.
Yeah, yeah. Okay. Well, we haven't heard any update from the Zoom people as to whether or not it can be heard. What? Tap on which microphone? Yeah.
What's wrong with it?
I don't know. Huh? No, we'll put it back where it was. Yeah.
I didn't know what Rand's complaint was.
That they couldn't hear, but apparently they can. It is working properly. Good. Okay. All right. So it's traditional when you have a conference in honor of somebody, usually your 60th birthday or something. This is in memory of Fred Cohen, to have a talk on the work of so-and-so. And in this case, Fred had so much work over 50-year career, or slightly longer perhaps, that we have divided it. And so I'm going to do the first 25 years of Fred's talk, of Fred's work, sorry. So turn the page. I've never used this before, so we try. Okay, so Fred wrote his thesis while doing canoeing on the Mackenzie River. I don't know if he actually wrote it while he was canoeing, but anyway, he did a lot of the actual mathematics while on this canoeing trip. And the thesis, Cohomology of Braid Space, University of Chicago, 1972, advisor Peter May. And what we have here is the ordered configuration space, FMK, for distinct points ordered in a manifold M. And we have the symmetric group acting on it by permuting the points. And we have the quotient, which is known as the braid space, because its relation to the braid group is that the configuration space modulo that is an Eilenberg-MacLane space of type BK1, which is theorem of Fox-Neuwirth, which is before this, right? That was already known at the time of Fred's thesis. So Fred studied this space while canoeing on the river, and in his thesis, he computed this POM. And the motivation for this is that this is relevant to, Peter had already shown that the elements of this group determine homology operations on the degree Q homology of any n-fold loop space. So that was the reason for doing this. And this, besides in his thesis, this later appeared as part of Springer 533, which was mentioned earlier by Peter. This is homology of iterated loop spaces in Springer lecture notes. And Fred did the, as Peter said, very complicated case where K is finite. And Peter did K equals infinity. So then Fred did, besides canoeing, there was mountain climbing with Larry, who is here, Larry Taylor and Fred. And while mountain climbing, they discussed configuration spaces. And configuration spaces is a topic to which Fred returned many times throughout his career. So this began his work on configuration spaces, to say, in combination with Larry and with other people later. The initial work was perhaps done while mountain climbing. Now, I don't know exactly. Joe Eisendorfer did some of this mountain climbing as well with them. I don't know how they actually did mathematics while mountain climbing, but this is what I've been told anyway. I wasn't there. I didn't do any mountain climbing, except, yeah, okay. Anyway, okay, so Fred started with this, and he returned to this many times throughout his career. So let's do the next page. So at this point, we are branching into the talk that Peter already gave. I was going to say this, but as you can see, it culminates in what Peter has already said earlier this morning. So maybe I'll just sort of skip most of this page and say it's been done, right? So the point was that you define this space here, and the point is on the next page, we have a theorem which says that we have a stable splitting, right? So, so the splitting is, you don't have to go to infinity to split, but you need to go to some sufficiently large t to split off whatever number of pieces you may be interested in. Now, in such a case, so there are particular applications of this, right, for various combinations of choices of these functors, including the little n cubes as one of them, which is what leads to omega sigma n of x. There are other choices that lead to the splitting of the James construction, for example, and other things. And I would say that it has been stated, I think, by Peter and others, that maybe this theorem has not been fully exploited, that maybe there are other good examples that haven't been explored yet. But anyway, when it came to such splittings, Fred frequently considered the question of how large a T you need to split various pieces. This is one of Fred's favorite questions. And Fred had a reason for this. And we will see later some application where Fred wanted to know for a particular reason. It wasn't just idle speculation, how low a T could you do? Could you get a splitting? You wanted to know how many pieces came off because he had some particular use for splitting, for using a fewer number of spaces. So since it's been done earlier this morning, I won't go into as much detail as I had been planning, but I'll just go right on and go on to Princeton. So Fred graduated. He got a job at Northern State, Illinois, I believe still in the Chicago area, used to come back to Chicago for discussion sometime. And then he was at the Institute of Advanced Study as a visitor in, I think it was 1996, 97, I believe, yes. 76, 77, yes. And at that time, John Moore was giving a graduate course in the fall of 1976, which was on the work of James and Toda on the exponents of spheres. Now, Michael Barrett had unpublished, as a lot of Michael Barrett's work was unpublished, had given this conjecture. And conjecture was X is a co-H space, and if the identity in the co-H structure, looking at the homotopy classes of maps from X to X, if in that structure the identity has order p to the r, then p to the r plus 1 should be null homotopic on the double loop space of X. So it's a relationship between the order of the identity in homotopy classes of maps from X to X, where the H space structure, where the group structure is coming from the co-H structure, to the double loop space where the H space, where the group structure is coming from the loop space structure on the other side. And in particular, if you had that homotopy equivalence, then of course p to the r plus 1 would annihilate the homotopy groups of X. So Fred attempt to prove this conjecture motivated a lot of his work. And in 1976, he met John Moore and was giving the graduate course, and Joe Eisendorfer is here. And they combined to attack this problem in the case of the Moore space. So special case of X, which satisfies Barrett's hypothesis, would be where X is the Moore space, as it was known in that notation. The notation is due to John Moore. The P is named after Frank Peterson. And the, do I have the definition of P up there? P is up there at the top. P M of K is the space two-cell complex where you take its take a n-1 sphere and you attach a degree K map to produce a two-cell complex. And this has one non-zero cohomology group. It's also one non-zero homology group. John Moore indexed it with the upper notation by the cohomology group for reasons which were useful in studying the Samuelson product. So that notation, often with the Moore space, is written with a lower index when you have one non-zero homology group, and you write often written with M as the letter instead of P, and you write M lower something in a group, and that was a standard notation for the Moore space with a homology group. And because they're more interested in indexing it by the cohomology, they wrote it this way. So they had a plan, okay? Plan is to use, well, first of all, general property is that when you have product decomposition, if X is homotopy equivalent to A cross B, then you get a decomposition because the homotopy groups of A cross B are the homotopy groups of A, direct sum those of B. So they had a method that sounds very simple, but it's difficult to actually use effectively. And maybe they were the first ones to effectively use this method, which is basically to apply Whitehead's theorem, that if you have a map which is an isomorphism between simply connected spaces, which is an isomorphism on homology groups, then it's a homotopy equivalence between CW complexes anyway. So their idea is to localize at some prime P, because we're interested in this theorem. This is a statement about what's going on at the prime P. And the question was, well, they had a plan, well, a general method, shall we say, for constructing product decompositions. And the method is to, first of all, look at the homology, which is something that Fred loved to do. As you will realize, if you don't already, Fred loved to calculate. So the first thing you would do, you'd take your space X and you would calculate its homology, and you calculate it algebraically. You calculate it if it had multiplication, it was an H space, you calculate it Hopf algebra. Otherwise, you calculate it as a coalgebra. You would calculate the Steenrod operations or the dual Steenrod operations if you did homology. And then in this case, you would guess what it might be the product of, looking at its homology. So you'd say, well, the homology looks like it's a tensor algebra of this, tensor that. And then so you might guess what a y and a z might be, such that maybe X is homotopy equivalent to Y cross Z. So if you could do it, and particularly it's easier in the case where X is an H space, you then go out and find yourselves appropriate maps. And this is actually the hard part. You get yourself a map from Y to X, a map from Z to X, and then you combine them into X. You show that you got a homology isomorphism and then a homotopy equivalence. So that's a basic plan. And the problem with the plan, the problem with the plan, they used this plan very successfully and they proved some very spectacular theorems. So I would say that the plan is not easy to execute. First of all, you have to look at the homology. So you need complete knowledge of the homology to start with. Otherwise, you'll never guess the right Y and Z. And after you've got them, then you have to, good intuition, you select the Y and Z. The hardest step at all is to construct the right maps. You know what you want your map to do on homology, but constructing a map of spaces to actually realize some algebraic map is a hard problem in general. Almost no good techniques are known for this. All right, so that's their plan, and they executed this plan successfully in some cases, particularly this case here. So the question, first of all, let's look at the base case, P to the R, where R equals 1. By the way, I'm talking more about this theorem because this is the part I understand better, right? So Peter, I would have felt nervous talking about the part that Peter did, but luckily he's talked about that. So I will say more about this because this stuff I understand better. So where do your elements of order P squared come from? In other words, you've got this thing and intuitively you might say, well, it's got elements of order P. Why should it have elements of order P squared? The homology doesn't have any, right? So where do they come from? Well, the first thing they did was they separated, in some sense, an element from its Boxstein. You look at the pinch map, you take the Moore space, you pinch the bottom cell to a point, and what's now we have the fiber, which is the base now, which is the S2n plus 1, and then let F2n plus 1 curly bracket P denote the fiber, right? And so the effect of this is you sort of separated an element from its Boxstein. And that sort of, shall we say, exposes what's underneath. Now, I can't say that too much better, except to say, look what's happened if you look at homology with respect to the Boxstein. So homology with respect to the Boxstein, your Boxstein squared is 0, so you can take any space and you can take its homology with respect to the Boxstein. And what's happened here is you've got something in the middle which has 0 homology with respect to the Boxstein. That P2n plus 1 curly bracket P, it doesn't have higher P torsion. So if you look at the Boxstein connecting this thing, you think of that as being a trivial space, right? Boxstein, that one is 0. So you think of this vibration as being sort of going from a sphere to the loop space on a sphere, right? You got a contractible guy in the middle with respect to that homology. And intuitively, it suggests that the homology of the Boxstein, with homology with respect to the Boxstein, I guess I'm supposed to be able to use this to point. Oh, I'm supposed to be, actually, I can do this, but I give my joke. Okay. So, so we have here, so nowadays we get this fancy point. Oh, what happened? Oh, I see, I'm not used to doing this. Nowadays, you see, you do this. Oh, no, you don't do that. Well, I don't know what you do. What do? You go back. How do I get back? I don't know. Well, I won't do this. This technology is too fancy for me. Nowadays, Fields has invested in this fancy stick, and you could use this to point where you want. Now, you understand that when Fred was last here, they didn't have this fancy stick, right? This is an investment of the Fields Institute over the years. Fred, if you knew him, used to walk with a stick. And Fred used to use the stick for various things like pointing at the blackboard. And the other place the stick was very useful is that when we had the conference here at that time, this blackboard kept falling down. And Fred would use his stick to hold up the blackboard. So anyway, so I don't want to use this thing here because I don't know how to use it. I know how to use this new replacement for Fred's stick. We don't actually have a Fred stick here. Anyway, well, where was I? Okay, I was on the next page. Right. Okay, so where do the elements of order P squared come from? As I said, homologically, it looks like that fiber thing, the F, this guy here, looks like it ought to be something like the loop space on S2n plus 1. Now, in order to do these decompositions, it's easier to do it if you have an H space. Right? As I indicated in the last slide, you construct maps into X, you construct 2 maps, one from X and one from Z, but how do you combine them, right? So it's a lot easier if X is an H space. So they loop this, and now we talk about the loop on P2n plus 1, and we have the loop, we have this guy here, and what they did was they showed a decomposition of this by the method that I said. Now, what would you expect out of this is that it, with respect to the Boxstein, it's like a double loop space on a sphere, right? We had the single loop space on the sphere in the right here, and we've got this guy, which we think of as being contractible. So this is like a loop space, and now we've got this loop space. So this is like a double loop space on an S2n plus 1. Now, Fred knew all about that, right? That was iterated loop spaces, right? Simple cases, only twofold iterated. He had done k-fold iterated loop spaces on suspensions. So he knew all about that computation. So he knew that the homology of this was looked like that. As I said, it was a special case of stuff he'd already worked on. And so what they did was they produced this decomposition. that basically followed this pattern. And the homology with respect to the Bachstein shows up as there's something which is left. After you've taken the homology with respect to the Bachstein, you've got this stuff which is left. And in particular, that gives you elements of one higher order, because the homology with respect to the mod P Bachstein was already 0. You've already eliminated that. And then you get this rest of the stuff, which I will call the noise. And that is what's left over when you do this, and that's an infinite ledge of Morse spaces. So what you had to do in this was, as I said, you had to map each of these pieces into here, and they used Samuelson products and relative Samuelson products to do it. As I said, in general, this is the hard step in any of these decompositions, is finding the maps, and then they had this product decomposition. Well, so they produced, as I said, this theorem, the decomposing this fiber, and then you have a map from here to here, and that gave them a decomposition of this. And T here is kind of what sits after you sort of eliminate the common piece, and T sits in this vibration. So you have some vibration that looks like that describes the Morse space itself, decomposition of the Morse space. And that allowed them by induction to talk about Barrett's conjecture for this space. This, as it stands, P greater than or equal to 5, because remember I said that they had to use Samuelson products and you got Jacobi identities and so on, and there's problems at the prime 3. Now those problems were solved by Joe by looking at the error term in the Jacobi identity. So in fact, it got extended to P equals 3. So the original theorem was P greater than or equal to 5, but it looks like 3. Okay. So what goes wrong at P equals 2? Well, just about everything. In particular, the statement of the theorem wouldn't work if you didn't have Hopf invariant 1, because you're decomposing an H space, loop on F2MP plus 1 as S2N minus 1 cross something or other. So if you didn't have an H space at S2N minus 1, you couldn't even, the statement wouldn't work, we're clear. So P equals 2 is different. And we have this quote from John Friedlander: all primes are odd. 2 is the oddest prime of all. So anyway, so for P equals 2, as I said, it's a whole wealth of issues, starting with the fact that we don't have an H space in general. So you can't, if you look back at their statement, one of the things that came up was this, but you don't even have that, right? That by definition, maybe you lost the notation because I glossed over it. Oh, well, I don't know. How do you go back? Here. Yeah, notation here was this one, right? Y curly bracket K. You have an H space, then that was their notation for the homotopy fiber of the degree K map. That's the map. X goes to X to the K. It's homotopy fiber denoted this way. So, and again, if you didn't have an H space, that wouldn't make sense. So if you look to the statement of the theorem, it talks about S2N plus 1, talks about this thing. Well, if this isn't an H space, there's no definition of this, right? You have to have an H space in order to take the P power map. Okay. All right. Now, a byproduct of this is that you actually get a map from here to here, right? You look at the preceding page. Well, the preceding page is what you get by going this way on the clicker. Yes. Okay. So you have this thing here, and you have a connecting map from here to here, right? So out of this comes a map that they called pi, which goes from loop squared S2N plus 1 to S2N minus 1. And what they showed was that if you compose in either direction, you get multiplication by P. So where is it? Yes. So that seems to be on the next page, or is it right here? Yeah. Okay, yeah, right here. So if you compose in one direction, it's obvious. One direction, you get a map from a sphere to its sphere, and you see that it's degree P simply by looking at what happens on homology. The other direction is less obvious. You're now talking about some map, and it turns out this is the P power map from here to here. that was not obvious, right? So anyway, it turns out that way. Now, a consequence of this is that if you take any element in the homotopy groups of this, that if you look at this, what it says is that if you multiply that element by P, that it's in the image of the double suspension. This E means the double suspension from S2n minus 1 into loop squared S2n plus 1. So if you have a consequence of this is that any X, if you multiply it by P, there seems to be a P missing. You start with an X here, then PX is in the image of the double suspension. There's a typo here. That should be PX, right? So if X is in any element of the homotopy of S2n plus 1, then PX is in the image of the double suspension, which means that if you keep doing this, eventually you go back to S1, and then you know it's 0. So that says that if you multiply by P to the n, take any element except once you get beyond the S2n plus 1 itself, once you get higher homotopy, says that any element, if you multiply it by P to the n, you will get 0. So that was a fairly spectacular result here. It says that the consequence is that P to the n kills for every q greater than 2n plus 1. This kills this, and originally P greater than or equal to 5, later P greater than or equal to 3 by Neisendorfer. Right? Now, this was as conjectured by Barrett and Mahauld. I don't know that conjecture was ever written down. They didn't write down a lot of their conjectures, but this was improving on the work of James and Toda here, who had shown that P squared would have worked. So James and Toda said you could put P to the 2n here because they would have put P squared here, right, and become P to the 2n. So this is what happens for P greater than 2, and the question for P equals 2 is still open, which is to say what is the best possible bound for P equals 2. So as you may have heard or you know, Fred was a great believer in computation, which he was very good at, and he loved to do it. And I understand one of his roles in this computation, in this collaboration, was to do a lot of computation to see what ought to be proved. Now, okay. So on the way, now I have heard that it said the road to the truth, which is what Peter said. I changed this in my slides because somebody in the first workshop said that the t-shirt read computation is the way to the truth, but I don't know. I must say that I personally never saw this t-shirt. So I was a graduate student at Princeton at the time. The theorem was proved in Princeton, and then the amount of traveling I did at that point was only slightly greater than I do now, which is to say that epsilon is greater than 0. So, so I was not, Joe and Fred gave lectures all over the world on this, and I was never at any of them. So, so I never saw this t-shirt. Maybe he had 2 t-shirts, one of which said the road to the truth and one of which said the way to the truth. But certainly this t-shirt is a famous in anecdote, shall we say, and maybe Joe tell us what the t-shirt actually said. Did it say on the road to the truth, the way to the truth? You don't know what he remembers. Okay. Well, anyway, there was a t-shirt. I think everybody agrees on that. Oh, Larry, yes. Okay, Larry says it's the way to the truth. Okay, well, yeah, okay. I said, but maybe he had 2 t-shirts. I don't know. Anyway, the way to the, well, that's what it says here. Okay, so what they did was also they conjectured that the following should be true. So Barrett and Mahauld, among their other unwritten conjectures, specified that the homotopy fiber of the double suspension, which is known as W sub n. So, by the way, they called it C of n. Right? So there's 2 different notations. The modern notation seems to be W sub n, but what they called it was C of n. C of n or W of n is the homotopy fiber of the map E squared. So you take S2n minus 1 into loop squared S2n plus 1, and that defines the space. You can call it Wn or C of n. And Barrett and Mahauld had conjectured that that should be a double loop space. There should be some X, which gives you that. And then what they conjectured Well, you could calculate, if there were such an X, you could calculate what its homology would be. So naturally, Fred did this, and one sees that homologically, if there were such an X, it ought to fit into a fibration that looks like this. Based on homology, it looks like it should look like that. And what they conjectured was that there should indeed be a fibration that looks like this, such that the boundary map was the pi that they had constructed earlier. And they conjectured that this composition would be null homotopic, where this is the James Hoffman variant map, and that then the double loop space on this would be that. So number 3 here is a consequence of 1 and 2. I won't go into the details there. Progress on this was made in 1988 by Gray, who showed that it's at least a single loop space. So he constructed a space which d-looped once the WN. Conjecture was should be a double loop space, and Anik, who constructed the fibration in part 1, but was missing is the link between the two, which is to say, the thing does single d-loop, and the question is, Anik constructed a space, and is the double loop space on the Anik space equal, or is the single loop space equal to the first d-looping that Gray had constructed? By the way, I had been hoping that Anik would come. He's the only one that I'm mentioning here that is not in my notes here, who is not here or has not been here. There's Brayton Gray was here during the first workshop, and we have everybody else that I'm mentioning in this. And Anik, I was hoping he might turn up. He hasn't done math in 30 some years, but I have been in contact with him, and I let him know that this is going on. He has a lot of people who knew him then. I thought there was a chance he might come, but he hasn't. At least he hasn't so far. That's all I could say. With the week is still open, not over yet. Anyway, I mentioned earlier that one of the things that Fred liked to do was ask, how many suspensions do you need, right? So we have here that you can decompose loop squared in S2n plus 1. This was preceding the Cohen-May-Taylor decompositions. This is Snaith decomposition. This special case was already known. And what Fred asked was, you have one of the pieces here, that Moore space, and the question is, how many suspensions do you need to get that one? And Fred asked at the prime, localized at an odd prime, if 2 suspensions were enough, and because he could show that if 2 suspensions is enough, then you could complete this, that you could say that Anik space, that the double loop spawn Anik space is indeed the fiber of the WN. Okay. Yeah, that would imply this. By the way, we're talking about p greater than 2 here. Okay, so as we move on here to the 80s, one of the things Fred worked on were applications of this technique, shall we say. It wasn't just the theorem. They proved spectacular theorems, but they had a technique. And that technique was used successfully in the 1980s to prove several other decompositions where you take a space and write it as a product with various consequences. And one of the things that you have to know, if you're going to be in the business, as we say, of constructing product decompositions, you have to know what not to try. You have to know how you've reached a point where the remaining spaces are indecomposable. And this is a criteria that Fred pioneered, first of all, with Mahaold and Fred proved, I guess I'm wrong. I should make exception for people who are dead. John Moore has been mentioned and Mahaold is dead. I talk about people who are here, right? The people who are alive, who are at this conference. So Cohen and Mahaold constructed this theorem that atomic is a notion that they created, which was you have a degree 1 self map, and you show that if you have a degree 1 self map, it turns out to be a homotopy equivalence. Spaces with this property they called atomic, indivisible. And they showed many cases were atomic, and they and other people showed other spaces were atomic. This pioneered it, right? Eddie Campbell, by the way, was here earlier, so has no exception to my statement of people who were here. They showed that that this space is atomic, And then Fred was part of showing that this was atomic. And he chose not to be listed as a co-author, but there's a general theorem which goes for loop K of S2n plus 1 now. So one of Fred's goals was to see what could happen at the prime 2. As I mentioned, the original theorem decomposition did not work. I had my thesis, I showed that we have a decomposition of this, and that's how I showed the exponent for loop S3. And what Fred showed this analog here for the prime 2. So this is the direct statement. W2, remember, is the fiber of the double suspension here. And a consequence of this is that the homotopy of this is a retract of the homotopy of this, right? So I'd use this for the prime P to show that the homotopy of this is a retract of that, which sort of by construction, all the elements have order P. Here, you can see it's a bit different because the prime is 2, and this guy, shall we say, by construction, the homotopy has order 4, all elements of order 4. So a consequence of this is that the homotopy of S3, that all the higher torsion is, all the higher homotopy elements of order 4. That particular statement was already known from James, but the actual decomposition of the space was new. So, as Fred might have written it, theorem, Euclid. Yes, Fred liked to attribute theorems to Euclid or various other people. And Fred would also say it is proof, it is rumored that this is 0. That's another way of Fred. So if you've listened to Fred give lectures, these will be common statements that you would hear from Fred. Theorem of Euclid, this, it is rumored that that is true, and so on. These are typical statements of Fred. An important resource, I point out, is Fred's A Course in Classical Homotopy Theory, written in 1988. It was originally written when he was visiting Seattle, Seattle Notes. It got published. And this has a wealth of valuable techniques. And for the experts, it contains some problems, such as I illustrate one, which has not yet been solved. G2 is a Lie group. And I won't go into too much detail here, but you construct the space, and naturally, Fred, first thing he's going to do is calculate the homology of that space. And he calculated the homology of that space and observed that it looks a lot like this space that Gray and Gray had constructed, right? And he asked whether they are the same, and that's still unknown. Anyway, okay. So, but I think this is an important thing about Fred's work is that I said that throughout the 1980s, he was doing a lot of product decompositions, right? He was generalizing the work he had done with Cohen, Moore, and Eisendorfer. He was showing that other spaces were products. He was showing that various spaces were not products. He was trying to extend to the prime 2 some of the stuff which was known for odd primes. And that, I would say, is probably his main focus in the 1980s, but is by no means everything he did. And I think this is an important thing about Fred. If you were to look at Fred's work and you say, in the 1980s, he was working mainly on this. If you were to throw out everything on this and look at what's left, you would have as much as most people would have done in a decade, right? So this is an incredible thing about Fred, is that he might be working on one thing mainly, but the amount of output he put on in other things was just enormous. And I think Tony collected the math reviews of his papers, and how large was the
125 pages.
Yeah. This is just the math reviews of his papers, 125 pages. And this is largely on all sorts of topics, right? So, as I said, and his growing list of co-authors, as I said, which continued to grow rapidly, his willingness to talk to everyone, anyone he was willing to, he met, he would talk to them on whatever subject interested them, right? And he had contributions to make to all sorts of different things. So, okay. Well, moving into the 1990s, okay. So Fred is continuing to work on Barrett's conjecture. That sort of, I would say, motivated him. Every talk I heard him give, at least in the early part of the 1990s, was on Barrett's conjecture. He wanted to prove that if you had it, they'd already proved it for Moore spaces, right? They wanted to show that if you have a random CoH space, if you have the order of the identity having order P, then the homotopy group should have order P squared. And this is leading him to study combinatorial group theory. He wanted to look at homotopy class of maps from loop suspension X to loop suspension X, right? And he formulated a group, which is now known as the Cohen group, where you look at certain identities which hold regardless of what Y is, right? So universal identities, and when I say regardless of what Y is, I'm talking about only CoH spaces Y. So you have specific things that hold for that. And a consequence of being a CoH space is this composition here is null. So if that composition is null, then you have these Samuelson products, iterated Samuelson products. And if any two elements are equal to each other, then this becomes null. So that's a property which happens if any I is equal to j for any I here equal to some j, then this will be null in here. So he studied that group. He studied the group of generated by these things, and that got called the Cohen group. And as I said, every lecture that I attended on it, and his proof never materialized, but that's not to say the work was useless. I mean, he did a lot of stuff. Unfortunately, we don't have a copy. So as I said, in his lectures, he mentioned certain obstructions, but I don't know what they were. He may have told me once, but I don't have a copy. He'd no doubt done reams of calculations, and indeed, as they say, people remember him, remember that file. G. Wu says he remembers Fred walking around with a big file of collections notes, and nobody seems to have a copy. So unfortunately, the file was too large to fit into the notebooks, in the margins of their notebooks. No one seems to have a copy of Cohen's lost theory. So whatever. Fred confided in me that he's starting to doubt whether it was true, actually, in general. But again, this is unknown. He started to concentrate his attention more on this special case where Y was a smash product with a Moore space. He was starting to doubt maybe whether it was true in general, but he was not able to prove that special case either. Right. So, as you see, he devoted a lot of his attention to Barrett's conjecture, but that did not prevent him from publishing oodles of other stuff. Lots of other co-authors, enough to make most mathematicians proud, just ignoring the stuff he did on, and in fact, a lot of the stuff on the Barrett's conjecture was never published anyway, but he certainly produced a lot of output in the 1990s. And some of you who weren't here, which is probably most of you who weren't here when I gave my introduction to the first conference, might not get the reference here about this. You'd have to replay the tape of the first lecture to hear the story of the encounter with the student. Well, I'll just say is walking by. I'm walking along with Fred, and Fred, as he talks, says, well, suppose you have a group. And there's a pause, and some guy on the street says, well, just any old group? Don't you have any hypotheses? And then Fred stops and talks to him for half an hour, you know. So, so Fred liked groups. And here's an example. We have here, when you have a normal subgroup, we have something called the plus construction. And the history of math emphasizes that you got to ask the right questions. That can be important. So question that Dave Benson and Fred asked is, what about BG, omega BG plus? And one of the theorems that he proves was that these guys have resolutions, what I call spherical resolutions. As you map to a sphere, you take the fiber, you map that to a sphere, and so on, and you get a finite resolution over spheres. So Fred had shown this for, I guess, BA5 plus, BA6 plus, BA7 plus. These have resolutions using these guys. And remember, these can be fibered over spheres, right? So these in turn have fibers over spheres. So this T is the one I mentioned earlier, occurred in the Cohen-Martin-Eisendorf decomposition, this guy, and these have fibers over spheres. And So they asked, well, Fred and Dave Benson asked whether it could be true in general. And I guess he asked Rand to consider this, and Rand eventually found a counterexample to this. But as often is the case, the fact that the theorem or that the conjecture, if you can call it a conjecture, never turned out to be correct doesn't mean that it was useless, right? You can now divide groups, shall we say, into those for which it holds and for which it doesn't hold, and then you can try and study their properties. So he loved to calculate. Here's the actual theorem. He talked to Dave Benson a lot, and this is their only published paper. They calculated the cohomology of this Hilbert series, as I will write down, gammas group path components, and they calculated the Hilbert or other Poincare series of the classifying space. There's the result. One thing which I should say is that Fred passed along a lot of his knowledge, and I think that a lot of this this stuff was passed along to Ji Wu and I about the use of finding idempotence in a group ring to construct splittings. And that was one of the things that Ji Wu and I made great use of in our memoir. And again, there are some papers like the one that I mentioned earlier on the decomposition of loop KS2n+1, where Fred was very much a part of it, but chose not to be listed as a co-author for whatever reason. So Fred certainly influenced a lot of things. We talked about 125 pages of reviews of his own papers, but he certainly influenced a lot of other papers in which he was not actually listed as a co-author. Anyway. But here is, I think, a striking theorem. As I said, he continued to study braids and configuration spaces, and maybe I've gone a bit beyond my 25 years. I hope I don't go too much beyond my time limit. But this is going to get in 2002, I believe. There's an incredible theorem to me about the relationship in braids and the homotopy groups of S2. So what's called a Brownian braid is braids on n strings, which become trivial upon the removal of any strand. And you have this theorem that says there's a differential from, there seems to be, yeah, from Brownian of any degree to any degree 1 minus less. And the homotopy groups, so you take homology with respect to that, and you end up with pi n of S2. So, so that was one incredible theorem to me. But I should say, as I said, that doesn't believe that Fred didn't have standards. The fact he would talk to anybody who's interested, especially strangers who wonder whether he has any hypotheses. But that doesn't mean he thought that all mathematics was good, right? He wasn't willing to accept just anything as being, even if it was sort of unpublished and, a new result. If it did not live up to his standards, he would denounce it and say, this is a crock. That was one of his expressions. Okay, so I'm not going to sing this, but I will mention some of the things that Fred liked to play with. So one of them is eta upper star. He loved to talk about eta upper star. Doesn't mean he necessarily had any theorems on it. It's like something he'd like to talk about. Eta upper star mapping from, so this is, you take the Hopf map from S3 to S2 and you dualize it and you get a map from loop squared X into loop cubed X. That was one of the things that Fred liked to talk about. He loved this Dinkenspeck-Weber relation, which certainly that Ji Wu and I made heavy use of. That's map that inserts brackets from left to right or from right to left, either way. So you take a sequence in a tensor algebra, sequence of points, and you insert brackets, and you get another element which you can expand out and apply beta again. And beta squared is n times beta. That's a relation as is known as the Dinkenspeck-Weber relation. There's a very short proof of this by Serre. There's a much longer proof if you don't use Serre, right? Just 5 pages and 10 pages in Magnus's book. We have the image of beta, which is ln of v, which is a classical object. And we have Li-n, which is the subset of these brackets where these guys are all different. And these are objects that he liked to talk about. And they were studied by other people as well. But now this one has come up earlier. He liked to combine objects. You have an object for each n. So you'd like to combine them into a simplicial set. And this is something which came up in Alejandro's lecture, right? You have commuting n tuples for every n. Well, it's not just that you have them for every n. You can build a simplicial set by looking at what happens to union over all n. So similarly, he liked to talk about the total 16 rod operation, square zero and so on. Cayley-Dixon algebras. So Cayley-Dixon algebras is this formula. You start off with an algebra over A, and you make an algebra over A direct sum A according to certain formulas. You need on A, you need a conjugation, and that's what all you need. And when you do this, you start with the reals. You end up next, you get the complexes, then you get the quaternions, then you get the Cayley numbers, and then you get something in degree 16, which is known as the Sedenians, which have zero divisors. So it's not norm preserving, unlike the preceding ones, but you can get them for every n. So he'd like to talk about those. And there's the Confritti theorem was another one of his favorites. And again, he would try and find analogs for these things in some of the things he did. So I think that maybe that is the end. Okay, so thank you.